Today we'll be talking about the triplet loss, and to showcase it, we will be using the Omniglot dataset. Now, why is this dataset an interesting one? First of all, if you look at the shape of the training set, you're going to see that we have 964 characters, and for each one, we only have 20 examples. So that's the opposite of what you would expect when you want to do a classification task. Normally, in a classification setting, you would have lots of examples for just a few classes. Furthermore, if you look at the test set, you will see that we have 659 characters, so 659 classes, and all of these classes are new, are different from the ones that we've encountered in the training set. So basically, all these images that we have in the test set are brand new images that the training set didn't contain. Again, in a normal classification settings, you would expect that the images in the test set are closely related to what you would see in the training set. So by training on the training set, you would have the knowledge required for classifying the images seen in the test set, which is not the case here because all the images are new. So how would we approach this? Well, we're going to use one architecture and a loss function. So we'll be using a Siamese network that's going to be trained with triplet loss. The main idea, if you look at the training set and the test set, is that you're not able to actually do classification, as I've said, in a regular setting. So what you would want to do instead is try to learn a similarity function. So to be able to say that these two examples are the same, or these two examples are the same. So basically, to have an architecture that can receive two examples and you would have the output saying yes are the same or no, these are not the same. In actuality, what we're going to do is we're going to have triplets. So we're going to have the input of our network will be composed of three elements. One will be called the anchor. The second one would be a positive example. And the third one would be the negative example. So, for example, let's say this is one image, this is the other image. So the positive example is part of the same class with the anchor, and the negative image would be something different, let's say an M. So with these three images, which let's call them a triplet. So with these three images, you would send all of them through the same network, the same architecture. And this is the idea of a Siamese network. We're going to reuse or share the weights for the first input, the second, and the third input. And as a result, we're going to receive three outputs. The first output would be an embedding for the anchor. We're going to have an embedding for the positive label and an embedding for the negative one. So this would be the metric network. And as an output embeddings. And then we expect to be able for these embeddings to have the following property. These two, so the embedding of the positive and the anchor, when computed through a distance function, we expect it to be less than or equal to the distance from the anchor embedding to the negative embeddings. As I've said, because we're sharing the weights of this network with different inputs, we'll call this a Siamese network. We will like to have this network that will be able to say that for these three examples, the first two are the same and the first and the last one are not. And by doing this and by training it in such a way that we have satisfied this condition, we will then reuse the Siamese network or the metric network for comparing only two examples, one at a time. So we're gonna later on take the Siamese network and input only only two images. This is the query image, and this is the target image. And we're going to, again, through the CME's network, we're going to receive two embeddings. And from these, we're going to compute the distance between the target and the query. And if the distance is above the threshold, then we're going to consider them that they're different. So how would we implement this? Well, let's start with the Siamese network. We're going to use Keras for this. So we're going to instantiate a sequential model. And the first thing that we're going to do is have a layer that will normalize the image, because the images, let's see the images a bit, have the following shape. So in the training set, we have 19,000 examples of images that are 105 by 105 by 3 color channels. So because we have images here, all of the values sit between 1 and 255. So they're pixel values. And we need to convert those to floats. So we're going to implement a single lambda layer here. And the lambda layer would receive a lambda function that will just divide all the values of that image by 255. So we end up with float values between 0 and 1. So we're gonna cast the input image to floats. Float 32 actually, and we're gonna divide that by 255. Because this is the first layer in the sequential model, we're gonna also say the input shape, which is 105 by 105 by 3 color channels. And then we're going to implement something really quick. It doesn't really matter how many filters we have in this instance, and the architecture in itself, it's not that important. So let's just keep it simple for now. So let's put a kernel size. The padding, we expect it to have the same output dimension. And let's put activation. Ready. And because we want in the end to have an embedding of a certain size, we need to downsize the image as we move throughout the network, because in the end we don't need all those pixels, all the full size of the image, so we need to downscale it, and we're going to use max pooling for this with, I'm not sure, let's say a 4x4 full size. We only do this, then we're going to still need to downsize this, because let's say that I'm expecting an embedding size for each input image. I'm expecting an embedding size of 32. So for achieving this, we're going to have to do this a few times more. Okay, I think one more will do. Okay. So we have this convolution, and then we reduce the dimension, and then we have another convolution, and then we reduce the dimension again, and then we have another convolution, and then we reduce that again by 4, and we're going to end up with the 1 by 1 pixel filters and 32 filters. I'm going to replace, just for the sake of having this embedding size used somewhere, I'm going to put that here. Now, of course, I could have used different filters here. I could have said 16 or 64. What I'm actually interested in is in having the last convolution layer being of a fixed size, and that's given by the embedding size. Okay, let's give this network a name. Let's say it's called a metric network. And let's say metric network here. Also notice that we only have 8,000 parameters or so. So by looking at the amount of variation from the images, it's going to be a challenge to have a good model that can work on these, but we're going to see the outcome at the end. Okay, we have this Siamese part. Now we need to define this full network that receives 3 inputs passes all these inputs through the CMEs network and then outputs 3 embeddings. Let's see how we do that. Let's say that we have an input, that's the anchor input, and we're going to use for this part the functional module of the Keras. So the CMEs network, we've used the sequential model, and we're going to use the functional style here. Okay, so we have an anchor input, and then we're going to have 2 more of the same, which we're going to be the positive and the negative inputs. So these would be sent through the metric network, and so we're going to have to pass, for example, the anchor through the metric network, and we will have an embedding. And if we do this 3 times for each, we're going to have embeddings for all of them. Now what we want is to have a model that can output the 3 of them in the same tensor. And this is important to have it in the same tensor, because otherwise, if we're gonna put all the outputs in the outputs list of the Keras model, then the training will behave differently. We'll have 3 loss functions, and the backpropagation will be done through all of them. So we don't want that. We want a single backpropagation with a loss function, a custom loss function that is able to reason about the 3 of them at once. So we're going to have to put them into the same tensor output. And to do this, we're going to have to stack them. So we will implement a new lambda layer that's going to call the backend stack function. And we want to stack them on the first axis. Okay. So this would be the output. This would be our output. And I can say that we will send the embedding for the anchor and the embedding for the positive and the embedding for the negative examples. But because we don't really need these, I'm going to put them here. Now we can compile the model and see how it looks like. So the inputs are the anchor input, the positive input, and the negative input. And the outputs will be this output tensor. Okay, so let's display this in a fancy plot. Let's say that we have some settings here that will show the parameters, show the shapes, and we want also the expanded nested model, which is the metric network. We want to see that expanded. Okay, so we have images. We have 1, 2, 3 images. Maybe we can name these as well. Let's say this is the A, this is the P, this is the N. So we have A, P, and N. Then we have the sequential, which is the metric network. They all pass through the same network, and we end up with 3 nodes, 3 embeddings actually, which are then concatenated, but they're concatenated slightly differently than I'm expecting. So I don't like to see the result of the max pooling as 1 by 1 by 32. So I'm gonna flatten this. And since we're at it, let's see if I can also add a name to this. So this model. Okay. And then if we run this again, so we have the A, P, and N that pass through the metric network, and the metric network outputs the batch size, and for each element in that batch size, 32, an embedding of size 32, and then we have 3 embeddings as an output from A, P, and N, and then we're going to concatenate these on the first axis. So we're going to have a tensor with 3 embeddings for each example in the batch size. So that's it for the network. We're done modeling this. Now, let's see how we will model the triplet loss. First of all, let's define a function that will output these triplets. And the idea is that we want to get those three A, B, and N examples through a function. So let's say that we'll call it get triplet. The data part is the data structure where we store the images and the classes. What we're going to do is, broadly speaking, we're going to select two types of classes, the positive class and the negative class. So we're going to select them randomly from all the available classes that we have in our data structure. So random number between 0 and the maximum number from the data keys, the keys containing the name of the classes. And because we want to select two values here for both the positive class and negative class, we're going to say that we want a tuple of size 2 as an output. Okay, so doing this, we will receive two classes, and then we're going to select A and B from the P class. So from all the indices that are part of the P class, we're going to choose without replace. And again, we're expecting two elements, A and P. And then we only need to select N from that negative class that we just selected above. So we're going to select a new random number from that one. Random choice from the elements of the negative class. Okay, so we're going to return A, B, and N. And let's see what we have. So we're seeing some numbers, and thankfully we have some util functions that will be very useful in a moment to see what's in those IDs. So we're going to print these and we're going to display the triplets. But before, we need to convert those IDs to images. So we're going to have to fetch the images from those triplets, or what, the same triplets. I'm not sure. Let's not say that these are the same triplets. Let's just ignore that for a moment. So we're going to have some triplets here, and we're going to extract them as images, and then we're going to pass these three images through the display triplet function. And I think I have a typo here. Okay. So what we have now, we have three images. We have the anchor, the positive, and the negative, and you can see that they're somewhat similar, the anchor and the positive, and the negative isn't similar at all. So I was saying that we need to enforce this inequality. Writing it in this way, like the distance between A and B has to be less than or equal with the distance between A and N, means actually that we can write it as the distance between A and B minus the distance between A and N needs to be less than or equal to 0. And all of a sudden, this is a loss function. Because if we want to minimize this, having this property go to 0 for all the triplets that we have, A, P, and N, then that would mean we have a network that can distinguish between P and N given A. So that's really nice. Except that there's some edge cases that we need to think about. One of which is the following. If, for example, let's imagine that we have two images, Y1 and Y2, and whatever these images are, Y1 and Y2 from the data set. So if we always have two different images, Y1 and Y2, and somehow our distance computed with these embeddings is equal always to 0, then our loss function there would be satisfied because we would have 0 minus 0 is always 0, which is below or equal to 0. So if by chance the network which will be fed into the distance will somehow make this distance be 0 for every pair of images, then that means that the network cheated. And one way for this to be satisfied is if the network, which is, let's say, the network output is f of y1. If f of y1 is always equal to f of y2, then whatever the distance we implement here is going to be always 0. So there's a way in which the network can cheat. And because it can cheat in this fashion, we need to add something different to it. And we're going to we're going to change the loss function to be the distance between A and B minus the distance between A and N plus a margin value, which is a hyperparameter. It's a number that we add there in order to force the optimization not to make these equal. So that's one change. Now, you may think that we haven't defined actually the distance, this D between A and B. We have some embeddings, and we can imagine that the embeddings are actually these A and P or A and N values. But what exactly is the distance? And we can say for now that this is only the Euclidean distance, and maybe in a future video we'll change that to some other metric. So if we say that the distance between A and P is the Euclidean distance, then we can define that as the difference, pointwise difference between a equivalent indices from A and B, and square that difference and then sum up all those squares. So that's the Euclidean distance between A and B. And then if we translate the distance between A and N again, we can say that's the sum between AY minus NY squared plus the margin. So that's our new loss function. And because we want to minimize that, there's always a chance that if this loss function is actually working correctly, it's going to be going below. And having a loss function that outputs negative numbers means going in the backpropagation step with negative numbers, which will basically reverse all the optimization that we have up until that point. So we don't need to have negative loss values. We're going to change that with saying that if this term is above 0, we're going to use it. Or if it's negative, we're going to output 0. And this is the final loss function. This is the triplet loss function. Let's implement it now. Say we have a function. Just one side note, we need to implement this triplet loss function by using the operations provided by the Keras backend, because the values that we're going to receive in this function will going to be tensors. So we're going to have to work with those primitives. The signature for a Keras loss function is y. So we have two inputs, the true predictions and the actual predictions. Now, if you were paying attention, we actually don't need, or we don't have an y true value, because the labels are actually contained inside the triplet. We know by the order of them that these two should be the same and these two should be different. So we don't actually need a label here. So we can say that this is an anonymous variable there. So let's quickly implement what we just described here, that function. So first of all, we need to unpack from the output, we need to unpack the three elements, the embeddings for the anchor, the embeddings for the positives, and the embeddings for the negatives. So we're going to say we have f a, f of p, and f of n. And these are from the predictions, from what the network outputs. We need all the examples, so we need all the batches, and we need the element 0 from the axis 1, which is basically the first embedding for the anchor. And then we're going to have the second value of the embeddings will be the embeddings for the positive, and the last one is going to be going to be the embeddings of the negative inputs. Okay, so we need to do a difference between of A and f of B. That's the first part, and then we're going to have to square that difference, and then we need to sum that up. And we will have to sum it up on the last axis because that's the reduction of the embedding dimension. This is the distance between A and B. Now we need to do that the same for the distance between A and N, but changing the P with the N. Okay, so now we can say that we need to have the distance between A and B minus the distance between A and N plus the margin, which we haven't defined, but let's put that as a parameter. So that's the loss function, and we need to do a maximum between this value and 0. And I haven't found a maximum, but we can replace that with a ReLU because it's actually the stuff that we're looking for. ReLU is either our value if it's above 0 or 0 if it's not. So it's exactly what we need. So we're going to pass that through ReLU, and because after the ReLU step we now have a bunch of loss values for each example, but we have actually a batch here, we need to aggregate this into a single value for the triplet loss. So we're going to reduce the batch values to a single number by using a sum. And then this is actually the loss function, and we're going to return that. So that's the triplet loss. Now, the only thing that we need to do is train it. But in order to train it, we need to have a generator that will generate batches. Why do we need that? Well, if I were to do auto compile, we can say loss is triplet loss. And let's spell that correctly. And fit generator. Now, if I'm going to use fit generator, I'm going to need the generator here that will use get triplet indices function and will generate of triplet images. So I'm still going to need something that's going to use this simplistic function that I wrote that just generates one example. So let's define that generator. It's going to receive some data structures like the images and the data structure that contains the classes, the class IDs, and the elements that are part of those classes. And let's say we also have a batch size as a parameter. Let's say we have 32. So we're going to initialize our numpy array, initialize with 0, and we need to define the shape. We expect, of course, to have as many rows as the batch size, and then we need to have triplets. So we have 3 elements there of images that are all 100 by 4, 100 by 4 by size 3. And the data type for this numpy array should be, of course, unsigned int 8 because they're pixels. Okay. We also need the Y. Fit generator needs to output a tuple of size 2, one of which is input batch, and the second one is the labels. But as I said, we're not going to use labels, so we can output anything we want here, except for the fact that we need to match the size of the batch size. So we can output zeros or the same batch size. Okay, and let's make this a generator that is running forever. So on each step, we need to generate a new batch. And we're going to iterate on all the numbers from 0 to batch size. And we're going to reuse that numpy array above. And on the index y, the current index, the current iteration, we're going to say that on the element 0, which is the anchor, we're going to put the image that's the A image. And we don't have the triplet generated here, so we need to first generate A, B, and N using that get triplet indices from the data. So we now have the indices of the triplets. So at the 0 mark where we set the anchor images, we copy the image into the numpy array. The image in the current iteration that should be in the place of the positive image is replaced with the positive image, and we're going to do this the same with the negative one. Okay, and now we only need to yield. There's also a quirk on how fit generator works. It expects that if we have 3 inputs, the first element of that tuple should be a list of the individual elements. So we need to scramble the values here a bit. So we have to say that the yield would be 2 things: a tuple, that's going to be 3 inputs actually, the index 0 of the second axis, and the images of that, the positive examples, and the negative examples, and the y. So maybe this is a bit confusing, but let's see what we have. If I'm having a single batch from this generator, let's instantiate the generator with a batch size of only 2. Now, batch would be a tuple with 3 elements. So we have these 3 elements. Let's take the first triplet. We have 3 lists here in the batch. The first list contains the anchors, the second one contains the positives, and the third one contains the negatives. Because the batch size is 2, we have 2 anchors, 2 positives, 2 negatives. So the triplet is composed of the first list with the first element of the second list and the first element in the third list. Equally, okay, I have typo here. Equally, the second triplet is going to be the second element in the first list, the second element in the second list, and the second element in the third list. And let's see the triplets. Second triplet. Okay, so we see the anchor in the positive, the negative, again, anchor, positive, negative. Now we all need to do is fit and use the generator. So we're going to use fit generator with the gen batches. We're going to have to provide it with all the data structures that it needs. And we're going to say that we'll put a batch size of 64 because we're on a GPU instance, and we're going to have to provide it with some steps per epoch. Now, because this is a forever running generator, we can say whatever because we don't actually have an end of epoch. So we can say that we need 20,000 steps, or we can say 5,000 steps and 5 epochs or 4 epochs, but this is basically this is the same because we're going to randomly generate triplets and we're going to stop whenever the epoch stops, which is defined by the number of steps. Okay, so hopefully this is going to run correctly and it should be starting to optimize in a bit. Okay, so we see this loss function is going down. We're going to have to wait for 7 minutes. So I'm going to pause this video and then I'm going to resume it once this is finished training. I'm going to paste a bit of code that I've just written. And this will generate a single batch that contains 4 elements, and it's going to present the embeddings and the distance between the triplets. And you're going to see how that looks in a moment. Okay, so whenever the distance between the positive and the negative is wrong, we're going to have the wrong message here. And whenever the distance are correct, meaning the distance between the positive and the anchor is lower than the distance between the anchor and the negative, we're going to have an OK. So these are the values of the embeddings for the anchor. These are the embeddings for the positive, and these are the embeddings for the negative. As you can see, the distances are computed using the same Euclidean distance as we have in the loss function. And you also can see the images. So this is okay. The distance between them is 0.4, but it's still lower. This is okay. This is okay. And this is okay. So we have all four of them correct. Now, at this point, I would say that the network is trained not sufficiently well, but it's still useful as it is. So we can try to have some other few visualization over it. Now, since we have it in this form, actually we have the Siamese network that we can use. We can use it in this way where we have, as I've said, the target and the query image. Or if we have lots of images, we can compute the embedding through the CME network of all the images, and then we can compute the pairwise distances between all the images to all the other images. And we can do a rank and see what are the most common images for each individual one. So what I'm suggesting is computing a similarity matrix, and we're going to use some function from scikit-learn that's called Euclidean distance. It's found in the metrics module and pairwise distances. So we're going to import that. Euclidean distance. So we're going to compute, as I've said, the distance between every image and every other image in the training set. So we have the metric network as an input and the images that we need to compute the similarities for. So the first thing is to use the metric network to predict the embeddings for all the images. And we're going to have image embeddings here. And then we're going to use that function from scikit-learn, Euclidean distances, and we're going to pass the image embeddings. So at the end of it, we're going to have a similarity matrix. For distances between one embedding and every other embeddings. Let's see what this does. Let's plot this a bit. Plot. I'm expecting that if I take a 10 by 10 slice of that similarity matrix, I'm going to at least have the first diagonal being all ones, if I did this correctly. Because, yeah, because the distance between one embedding and itself, it's going to be 0. Okay, now that we know the similarity matrix is computed correctly, let's use another utility function to plot the similarities between one ID, let's say 7, from the test images, and using the similarity matrix to retrieve the top 10 most similar images to it. Okay, so this is the output. What you're seeing is elements that are green are actually elements of the same class with the target. So this is the target. This is the 7th image that we queried. And these are the 10 most similar images to it by the embeddings. So all these 10 images have the smallest Euclidean distance between their embedding and the embedding of this target image. And if you're looking closely, I would say it's working okay for the runs that we left it to train. Also note that we have among these 10 most similar values, we have 1, 2, 3, 4, 5 correct. And I will find that we only have 20 elements that are actually part of the same class with this one. So that's a good result. Even more, if you consider that these elements that are among the 10 most likely to be similar were chosen from the rest of 13,000 examples. So we have 13,000 examples, and the top 10 of them, most of them are part of the same class. The last step would be, let's print more examples, like more characters, to see how this is working. Let's see, if I'm gonna enumerate some IDs here. Haven't picked them up beforehand. I'm just making them up right now. 234, 567, let's say 879. Okay. And one more. Okay. So if I have some IDs, let's do the thing that we did above. Let's plot the similarities between this, test images, test data, the similarity matrix, and the top 10. Okay, so except this class, which didn't contain any correct values, all the others had pretty decent results. And if you squint, actually, some results look plausible to me. Like this one and this one looks quite similar. These two again, and I would say also this one is really close. Maybe this one is plausible as well. So yeah, I'm not too disappointed by the results. Let's say we can plot more example for each one, let's say 28. And maybe we will have more matches between them. Yeah, so this one is really actually nailed it. Okay, we have one positive in that strange class, and maybe with a few more training rounds, we can get that to the top 10. So overall, I would say this worked surprisingly well. In order to do classification where you have few labels and lots of classes, you can employ this triple loss by training it in such a way that the distance between the pairs that are similar is lower than the pairs that are different. In future videos, I'm going to expand on this idea because this is the most simplistic way of doing it, and there's lots of opportunities to optimize when choosing the triplets, and there's some strategies that allows you to train faster by choosing the triplets in a different way, in a different format. Thank you for watching, and I'm hoping on seeing you on another video.